one thing there's an updated course outline. I originally said the next lecture is cancelled. No, it's the one after that that's cancelled. Okay, so next week we do have a lecture. Assignment 2 is due next week. The week after I'm not around. I'm in a conference in Calgary on September 26th. So there is no lecture and there is no assignment due then. And then assignment 3 will be due on October 3rd and will be based on next week's lecture. Alright, I have also updated this on eClass. I have put an updated outline. Okay? I apologize if you made arrangements. I'm not sure why I picked September 19th in the first place, but it's September 26th and I'm not going to be around. So just again, next week there is a lecture. The one after that is cancelled. And next week, assignment 2 is due. And I'm going to update the calendar on eClass as well. Alright, so today we are going to discuss, just before we discuss anything, did everybody submit their assignment? So the assignments are due at the beginning of the class whenever the assignment is due. It's due Wednesday at the beginning of the class. So today we are going to discuss matrices. What are matrices and what are they used for? So matrices will perhaps take us this whole lecture and also a little bit of next lecture. And then next lecture we're going to discuss what's remaining of the matrices and then the vector calculus. And then after that we are going to start the mechanics concept of the course, the mechanics concepts of the course, which are the stresses and the strains and the constitutive laws. So, what are matrices? So let's first try to understand what is a linear function. If I have a function defined from R to R such that f of x is equal to ax, where a is a real number, you will find that for every two real numbers and for every two other real numbers, f of alpha x plus beta y is equal to alpha f of x plus beta f of y. Because f of alpha x plus beta y is equal to a multiplied by a alpha x plus beta y. Because of the linearity of the operation, I can write it alpha a x plus beta a y, which is basically alpha f of x plus beta f of y. This is not true if, for example, f of x is equal to ax squared. If f of x is equal to ax squared, you will not be able to say that f of alpha x plus beta y is equal to alpha f of x plus beta f of y. This only applies for that linear function. Now let's try to extend this linear function from R to R and extend it to from R squared to R. Well, how can I extend it from R squared to R? I'm going to look at a vector in R squared is made out of two components. So I'm going to take those two components multiply the first one by a constant, and multiply the second one by another constant. So for every x, which has two components in R2, I give you a real number. I get that real number by simply multiplying the first component by a constant and the second component by another constant. So what? And indeed, f of alpha multiplied by the vector x plus beta multiplied by the vector y, this is for every x and y in R2, and for every alpha and beta in R, you'll find that this is still true. F of alpha x plus beta y is equal to f is equal to the constant a11 multiplied by alpha x1 plus beta y1 plus the constant a21 multiplied by alpha x2 plus beta y2. Because of the linearity of all these operations, I'm able to say this, if you rearrange, this will be equal to f alpha f of x plus beta f of y. Not only this, what you notice here is the way I constructed f of x, I introduced two new numbers, a11 and a21. a11 is used to multiply by x1, and a21 is used to multiply by x2. Now, if I consider a vector, because these are real numbers, so I'm going to consider a vector v that's equal to a11, a21. Then what does f of x equal to? It's equal to the dot product between this v and x. I'm going now to introduce another one from R2 to R2. So I'm introducing a function from R2 to R2. So the argument is a vector, and the result is a vector. Since the result is a vector, that means f of x has to have two components. The first component is a linear function. And the second component is another linear function. Okay, these have to, just for consistency, x1 plus a22 x2, where those a, I, j's are just real numbers, any real numbers, but fixed for this particular function. Similar to the previous example, you'll find for every x and y in R2, and for every alpha and beta in R, you'll find that f of alpha x plus beta y will be equal to alpha f of x plus beta f of y, and also you'll find that f of x is equal to a vector v1 dot x and another vector v2 dot x, where v1 is the vector a11, a12, let's use the comma, a11, comma, a12, and v2 is the vector a21, a22. So what I'm trying to show you here is the matrix. A matrix is nothing but a linear operator, a linear function acting on linear vector spaces. So for every So a matrix is nothing but a linear operator or a linear function from one vector space, from one linear vector space to another. The argument is a vector, and the result could be a vector, it could be a scalar, could be an n-dimensional vector, whatever. And a matrix in general T is a linear operator from Rn, let's say to Rm, it can be represented, any linear function can be represented by a matrix of numbers. Now this matrix of numbers will look like this. The argument is a vector. So T takes a vector that's m by 1 and gives you a vector that's m by 1. So it takes an n-dimensional vector and gives me an m-dimensional vector. The first component in the new vector is equal to the dot product between one vector and this. So this is equal to v1 dot x, where this is x and this is v1. The second component is equal to another vector dot x, which is the second vector. And the m component is equal to vm dot x, where this is vm. And that's why this matrix will be equal to m rows multiplied by n columns. And because of that linear operation, everything here is linear. If I put here alpha x, if I put here alpha x plus beta y, the result is not really dependent on the order of the operation. I can basically have alpha out, multiply t by x, get a vector, and then multiply beta by t of y, and get a vector. And this is only because of the linearity. This does not apply to other functions, only because matrix is a linear function. So a linear map, just a basic definition, a linear map between vector spaces V and W is a function that takes from one to another, such that for every 2 in the first, and for any 2 real numbers, t multiplied by alpha x plus beta y is equal to alpha t of x plus beta t of y. And this fact states that whenever you see something like this, whenever I tell you that there's a linear map between 2 vector spaces, if the 2 vector spaces are Euclidean vector spaces, then right away there is a matrix of numbers. When I choose a certain orthonormal basis set, right away there is a matrix of numbers that represents this linear map. So let's graphically see what a matrix does. So we have agreed that a matrix does the following. Let's call it the matrix M. Let's say M takes from R2 to R2. Any vector here, x, there is a vector here, y, that's equal to m multiplied by x. And there is another vector here that's called L. And there is a vector here that's equal to ml. And if there is a vector here that's equal to x plus L, then there's a vector here that's equal to m of x plus L, which is also equal to mx plus ml. So this is graphically what a matrix does. Because a matrix is nothing but a function, I'm always wondering if I can find the inverse of that function. So the existence or not of the inverse of the function depends on something called its kernel, especially for the matrices. The existence of the inverse of a matrix depends on what's happening to its kernel. What's a kernel? So as we said, a matrix will take vectors and give me other vectors. So for this vector might keep its length or change its length, might keep its direction or change its direction, but it will get a vector. Is it possible, or the kernel of the matrix are the vectors that when I apply m to them, they go into the zero vector. So the kernel of the matrix M, I'm just going to write the definition. Where M takes from, let's say, V to W, the kernel of M is X, where X is in V, and Mx is equal to the zero vector. It's all the vectors in the space here that go to zero. So example, let's look at the matrix M that's equal to 1, 1, 2, 2. You will find, just because I've done this before, 1, 1, 2, 2, if I put here negative 1 and 1, I'm going to get the zero vector. Because when I take the dot product of this vector with this vector, I'll get 0, and this vector with this vector, I'll get a 0. Or 1, 1, 2, 2, if I put here negative alpha and alpha, where alpha is any real number, I will also get the 0 and the 0. Because this will be equal to negative alpha plus alpha, negative 2 alpha plus alpha, plus 2 alpha, which is equal to 0. Now we know, or you should know, from previous linear algebra courses, that this M is not invertible. Why is it not invertible? Because it takes a lot of vector and takes them to the zero vector. So if you try to invert it, if you try to find a map that takes from R2 to go back to the original space, you can't find one map because zero vector corresponds to a lot of vectors in the original space. And if you actually look at it graphically, because of linearity, all I have to look at is a circle of vectors. I'm going to look at the circle of vectors and see what M does to it. What M does is you will find that M will take all those vectors and give you one line. And any vector in this here, x is equal to negative alpha alpha. Any vector here will be mapped to the zero vector. And so M minus 1 does not exist. On the other hand, M, or let's call it the matrix N, which is equal to negative 1, 1, 2, 2, is invertible. And you will find that if you draw a circle of vectors, you will get some sort of an ellipse of vectors. Or if this is a rotation, you might get a circle again. But you'll never get, because of linearity, you won't get anything else. You won't get any different shape. So the matrix takes a circle or ball for a higher dimension. So the kernel of this matrix, we just showed it, the kernel of M is equal to x, where x is equal to negative alpha, and alpha is a real number. This is a bonus exercise, and expect something similar to this. This should be an easy exercise. And to explain what this exercise means, let's go back to the graphical representation of the kernel. Whenever one vector is in the kernel, any multiplier of that vector will also be in the kernel. And that means that this kernel forms a subspace inside the original space. So just some definitions of functions, because we're going to talk a lot about whether a matrix is invertible or not. So we need to understand what's an invertible function and what's a non-invertible function. So the first type of function we're going to talk about are injective maps. And just an example, and I guess that those who are taking 665 have heard this on Monday, but we're going to say it again. So an injective map is one-to-one. Just an example of an injective map, just to explain what we mean. These are the students in 664, and this is the set of IDs in U of A. For every student, there is a unique ID. This function is not invertible because there are IDs that do not have students in 664. Because there are IDs that do not have students in 664, I cannot invert this function or this map. So an injective map, or one-to-one, assigns to every element, assigns it a unique element. So for every, so T from X to Y is injective, or one-to-one, if for every X in X, there is a unique element in Y such that T of X equal to Y. So right away, if a matrix has a huge kernel, it's not injective. Because if a matrix has a huge kernel, it means there's a lot of vectors that go to 0, which means that it's not one-to-one. It does not assign a unique value to every unique vector. Surjective maps, or maps that are onto, these, for example, just to explain what a surjective map is, again, students in 664 and gender. The possible genders are male and female. Now, in the class, there's a lot of students that are males, a lot of students that are females. This is a surjective map because it covers all my codomain. This is called the codomain. And the range is equal to the codomain, which means I reach every element in the codomain. This is not invertible because for every male, I can't find one student in 664 that's male. I have several, so I can't form a function that inverts this function. So surjective map or onto map or in other words, T from X to Y is surjective if for every Y in Y, I can find at least one X in X such that T of X equal to Y. So for every element here, I can find at least one in X, maybe more, such that T takes X into Y. An invertible map is both injective and surjective. So an invertible map, to find a map that you can invert, by definition, the only map that I can invert has to be both injective, assigns unique values to my original vectors, and surjective, it covers all my codomain. So this map, as you can see, is bijective. For every element here, there is a unique one on this other side, and for every one here, I can find the original element, and that's why this is called a bijective or invertible map. So an invertible map is both injective and surjective, or one-to-one and onto. So again, expect this might be a little bit difficult, this bonus exercise. This should be easy. So the easy ones, you can expect them in your midterm. And the hard ones too, just to see what you can do with it. But not to worry. So, what we're saying here, which is important, is that a map, or a matrix that's n by n, is invertible, is equivalent to saying that the kernel of that map is 0, which means the vectors that go to the 0 vector is there's only one vector that this map can take to the 0 vector, and that's the 0 vector. Because we know, of course, that any matrix M11, M12, M21, M22, when I multiply it by the 0 vector, I will get the 0 vector. So, of course, the kernel of M, or 0, always, the 0 vector, is always an element of the kernel of M. And the question is always, are there any other elements in the kernel of M? If there are no other elements in the kernel of M, and M is a square matrix, then it's invertible right away. And these are what those bonus exercises want you to show. So there are a few examples in your textbook. You can just, they're just repetition of what we were talking about, just to make the point clear. Any matrix is just a bunch of vectors, and the matrix is made out of the M of x is equal to the dot product between each row by the vector x. Another bonus exercise, now this one is a little bit difficult, so don't, maybe you can think about it, but you won't see this in the exam. But you still have to think about it because I'm going to get an easy part of it. But what this says is, for the matrix to be invertible, if it's an n by n matrix, all you have to know is, are these vectors linearly independent or not? If they're linearly independent, then right away this matrix will be invertible. Because if they're linearly independent, you can show that the kernel is 0, and if the kernel is 0, that means from the previous bonus exercise that it's that the matrix is invertible. So a few other examples, you might want to read them. And then at the end of today, I will show you a few tricks how to do things in mathematics. So a matrix, as we said, takes from a linear vector space. Let's call this U. And let's say that this is Rn, and this is Rk. From an n-dimensional vector space to a k-dimensional vector space. And I have another matrix that takes from this k-dimensional vector space to an m-dimensional vector space. So for every x here, I have ux, which is another vector that has k dimensions. And for this ux, I have another vector here that's equal to v u of x. And the question is there a matrix? One matrix that takes me from Rm to Rm, and I'm going to call this matrix Vu. And notice the order of the operation. The order is very important. I'm applying U first and then V. So V appears on the left. Because I apply U to the vector first, and then I apply V to the result. So I apply U to the vector and then V to the result. So if you probably know the multiplication of matrices already. U is n by k, and V is k by m, and the result is an n by m, where each element is equal to the corresponding row multiplied by the corresponding column, or the dot product between this vector and this vector. So this new matrix is called Vu. It's a new matrix that takes me from Rn to Rm. So throughout the course, the important matrices that we're going to work with are matrices that are 2 by 2 and 3 by 3. Most of what we're going to talk about applies for higher dimension matrices, but we're going to present most of what we're doing here for M2 and M3, because in continuum mechanics or solid mechanics, we're putting everything in R3. We usually, everything is usually in R3. Right, before I jump this, just a very important note. If, let's say, U and V take from Rn to Rn, the order is important. UV is not equal to VU. The operation V multiplied by the vector and then U multiplied by the result is not equal to U multiplied by the vector and then V multiplied by the result. And there are many counterexamples. Okay, so a lot of people always find the summation convention difficult, but the summation, if you heard about it before, but the summation convention is designed to make the manipulation of the formulas easy. So you have to think about it as an easy way for reducing the number, for reducing the number of words that you write actually on the page. So, as we said, if I have a vector in R3, I write the vector as x1, x2, x3. I also write it as x1, x2, and x3. And I have xi represents a component of x. And if M is a matrix, then M has this form, M11, M12, M13, and so on. Mij represents an entry in M. So what happens when I multiply m by x? M by x is a vector. It's equal to, if this is m11, and so on, and this is x1, x2, x3, you will get the sum of m1j xj, where j is equal to 1 to 3. And here the sum of m2j xj, where j is equal to 1 to 3. The sum of k of j equal 1 to 3, m3j xj. So this is the result of the operation. The summation convention allows me to reduce all this to saying that the vector that results, mx, the component I, is equal to the sum from j equal 1 to 3 mij xj. And whenever I see two repeated indices, I know that there is a sum sign here for j equal to 1 to 3, and I can remove this sign. As long as I see those two repeated together, I know that the summation is implied. And so all the above formula is now reduced to this formula. The component mxi, the component I, is nothing but mi and then sum over j. A vector u in a three-dimensional space, this u is equal to u1 e1 plus u2 e2 plus u3 e3, or is equal to the sum I equal 1 to 3 ui ei. I is repeated. I'm going to imply that this is happening, the summation is happening, just by simply writing ui ei. Because we're going to be using those indices for a lot of formula manipulation, there are some variables that we're going to use, and the first one, or some symbols that we're going to use. The first one is the Kronecker delta ij. Now I know that ei, if b is equal to e1, e2, and e3, is an orthonormal basis set, I know that ei dot ej is equal to 0 when I is not equal to j, 1 when I is equal to j. I'm going to put a symbol called Kronecker delta that gives me this value. When I is equal to j, I get 1. When I is not equal to j, I get 0. So I can write. Now I know that the identity matrix in R3 is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. A general component of I is written ij. This is the component in ith row and the jth column, this component is in fact equal to delta ij. Because when I is equal to j, I get 1. When I is not equal to j, I get 0. And this is in fact equal to ei dot ej. The alternator, this is a symbol that's used for the cross product. Because we know that the cross product depends on the order of the vectors, I introduced the symbol epsilon ijk, which has one of three values: 1, -1, or 0. This is when I, j, and k is a cyclic permutation of 1, 2, and 3. And this is I, j, and k is a non-cyclic permutation of 1, 2, 3 otherwise, and 0 otherwise. So for example, 1, 2, 3 is equal to 2, 3, 1 is equal to 3, 1, 2 is equal to 1. 2, 1, 3 is equal to 1, 3, 2 is equal to 3, 2, 1 is equal to -1. Epsilon 2, 2, 1 is equal to epsilon 1, 1, 3 is equal to epsilon 2, 1, 2 is equal to 0. Okay, so why do I need this? Because it makes life very easy. I'm going to go through some examples so that you understand why or how to use this. The first thing, whenever you're doing this, whenever you're using this summation convention, you have to know what you're dealing with. Is it a vector, or is it a matrix, or is it a real number? Because that will indicate what components you have to see. For example, u dot ei. We already know that u dot ei, we've started this before, is equal to the ith component. Of course, that's when we say that E1, E2, and E3 is an orthonormal basis set. Let's look at this. Whenever I multiply a matrix by a vector, if M is a matrix and U is a vector, MU is another vector. Now the MU is a vector, so it has one component. And this one component is obtained by summing Mij multiplied by Uj. And there is a sign, there is a summation sign here that's implied. Mn is a matrix. Since it's a matrix, it has two components. It has two indices, I, j. Those two components, so this is matrix M, this is matrix N. The component here is equal to the row multiplied by the vector. The row vector multiplied by the column vector. And that's why you get M, I, K, N, K, J. And there's a summation sign here for K equal 1 to 3, but we don't put it. Summation is implied. So the component MNIJ is equal to MIK NKJ, where I'm summing over K. So perhaps at the beginning, write the summation sign and then take it out. matrices multiplied by each other, M and K. The final matrix has components ij. I is usually the first free index that appears, because that's the row of M. Which row of M I'm talking about? And J is the last index that appears. These are the free indices. There is no summation. And the summation happens inside. So summing over K from 1 to 3, and then summing over L from 1 to 3. This is equal to the sum. Sum K equal 1 to 3, L equal 1 to 3, M ik, MKL, KLJ. And summation is implied. When you look at this expression, you'll find I and J are free indices, which tells you whether this is a matrix or a vector. Depending on the number of indices or free indices, you'll know whether this expression represents a matrix or a number or a vector. For example, v.mu, is this a real number or a vector or a matrix? Real number. Real number. That's the dot product between two vectors, v and mu. So that I expect no free indices. Indeed, v.mu is equal to the sum from I equal 1 to 3 of vi dot MUI, vector dot product between one vector and another. I'm taking the dot product, so I'm summing over the components of the first vector and the second vector. But the component MUI is in fact equal to MIJ UJ, where I'm summing from J equal 1 to 3. Summation is implied whenever the indices are repeated. You'll find this is equal to VI, MIJ, UJ. Which means this is a real number because I'm summing over I, summing over J. This is just one number. What does MII mean? Is this a matrix or a vector or a real number? A real number. What is it equal to? Yeah, go ahead. It's the sum. Don't forget the sum. So this is because I is repeated, then I'm summing. You have to put, whenever you see it one, you have to, inside your head, you have to put the sum sign. So there is a sum sign here from I equal 1 to 3, MII, which is equal to M11 plus M22 plus M33. All right, so we'll give you 5 minutes and we'll start exactly at 9. bracket, star, right comment, star. Yes. No, just the round bracket, star. Round. Very good. Let's round this line. I sent an email to you. So if he's not sitting there,
Okay, yeah, I'll talk to you.
yeah, I don't think he's in his office. But if there's stuff, it's not nice to just
Yeah, I'll email him.
Alright, so the determinant of the matrix is a measure of whether this matrix is invertible or not. The determinant of the matrix measures whether the rows of that matrix are linearly dependent or not. If the rows of the matrix are linearly dependent, then when you calculate the determinant, you're going to get a value of 0, which right away tells you that this matrix cannot be inverted. Again, if the rows of the matrix are linearly dependent, it means that the kernel of that matrix has a lot of vectors. When you calculate the determinant gives you 0. Right away you know, okay, well then this matrix cannot be inverted. And we will see this in both in matrices that are 2 by 2 and matrices that are 3 by 3. In a 2 by 2, if you consider that M is made out of 2 vectors, vector A, which is equal to A1 and A2, and vector B, which is equal to B1 and B2, if you define the determinant like this, A1 B2 minus A2 B1, so this is the definition of the determinant, you'll find that if A is equal to alpha B, where alpha is a real number, you'll find that the determinant of M is equal to 0. And if A is not equal to alpha B and AB are not 0, you'll find that the determinant of M is not equal to 0, which right away tells you that the determinant of M is equivalent to saying that M is not inverted. Which is equivalent to saying that there exists X which is not equal to 0 vector, X is in R2, and Mx is equal to the 0 vector. Which basically tells me that the kernel of X, the kernel of M, has many vectors that are not 0. So graphically, this determinant has also a function. This function is as follows. M is made out of the vectors A and B. When I multiply this matrix by 1, 0, when I multiply M by 1, 0, which is B1, I get A1, B1. So I get this vector X1. When I multiply M by 0, 1, I get the vector A2, B2. Let's just put it here. When I take the dot product of this with this, I get A2. Dot product of this with this, I get A2. And so I get the vector X2. Let's call this X1. Let's call this X2. The area here is in fact equal to the determinant of n. And because the area here is equal to A1 B2 minus A2 B1. And so the determinant of M tells me how much the original square area between the original basis vectors, how this area transforms under the matrix M. So it gives me a measure of how area transforms in R2. In R3, the determinant of the matrix is defined using the triple product. The triple product, which we studied in the end of last lecture, gives me a measure whether the three vectors are linearly dependent or not. If they're linearly dependent, then the triple product will be 0. So I'm measuring the determinant of M using the triple product between the three vectors, which is equal to A dot B cross C. And similar to the previous argument, and using the results of cross product section, the determinant of M is equal to 0 is equivalent to saying M is not invertible, is equivalent to saying there is a vector x which is not 0, x is in R3, and mx will be the 0 vector. Now, similar to the determinant of M in R2, the determinant of M in R3 gives me something about the geometry. If this is the original cube formed by E1, E2, and E3, if I find x1, which is equal to M E1, x2, which is equal to M E2, and x3, which is equal to M E3, then the determinant of M will be equal to x1 dot x2 cross x3 just by rearranging the formulas, which is equal to the volume formed by x1, x2, and x3, which is basically the image, or the volume, of the image of the cube made by E1, E2, and E3. So the determinant of M will tell me whether this mapping is making things bigger, making things smaller, if it's increasing the volume or is it decreasing the volume. It will tell us a lot of other things on the deformation as we are going to study in the third chapter. But for now, we see that the determinant, if I have some deformation or some object that deformed, the deformation is usually described by matrices, and those matrices will tell me what happened to the volume and will tell me other things as well. So for the proofs of these arguments, you can, the details of all these are in your book. And these are the two important arguments. The determinant is m of m is 0, m is not invertible. The vectors associated with m are linearly dependent. The kernel of m is the 0 vector. It's not the 0 vector. There exists a vector that's not equal to 0, but mx is equal to 0. And the opposite argument holds. The determinant of m also gives me the following. The volume here, I'm going to use capital letters. The volume here, if I have 3 vectors, is equal to the triple product between W, U cross V. The volume here, I'm going to use small letters. Is equal to the triple product between MW and MU cross MV. So I have a matrix M that takes those 3 vectors and gives me 2 new 3 vectors. So I would like to compare the new volume with the original volume. If you use the different, if you use the indices, you're going to find that the determinant of M is equal to the new volume divided by the original volume. So the determinant of M gives me a measure of how the volume changes locally between an object and once it's deformed, if that deformation is described by a matrix. And these are direct results from these expressions. The determinant of a matrix, or matrix that's equal to 2 matrices multiplied by each other, is equal to the determinant of the first multiplied by the determinant of the second. The determinant of a real number multiplied by a matrix, it's almost like putting alpha, or it's like putting alpha here, here, and here, which when you take it out will be alpha cubed. So this is equal to alpha cubed, the determinant of M. The determinant of I is the identity matrix, will be equal to 1 because U V or W and V will stay the same. And so the volume after deformation or after applying this linear map is equal to the volume before the application of that linear map, and the determinant is equal to 1. The transpose of a matrix is defined as follows. If M has M11, M12, then the transpose of the matrix will be equal to M11. You take every row and make it into a column. Every column and make it into a row. This is the definition that you are used to from your linear algebra courses. However, there's a more abstract definition that does not depend on the components, and this more abstract definition is very useful when we start proving formulas. So you really need to be familiar with this definition. The transpose of a matrix, if M is an n by n matrix, the transpose of the matrix M is the unique matrix that satisfies the following. For every two vectors in Rn, if I multiply mu, or if I take the dot product between mu dot v, it's equal to if I take u multiplied by the transpose of v. The matrix MT that satisfies this for any u and v is the transpose of the matrix M. These two definitions coincide for Euclidean vector spaces. But for the proofs, we're going to use this because this is much easier to manipulate for formulas. Few results from this definition right away. What's the transpose of those two matrices? You'll find the transpose of those two matrices is equal to M transpose, N transpose. The transpose of two matrices added to each other is equal to N transpose plus M transpose. Just to show you how to prove something like this, how it makes life very easy to utilize that definition. For every u and v in Rn, n m u dot v is equal to u dot nm transpose v. So I would like to find this nm transpose. Well, I know that n mu dot v from the definition of the transpose is equal to mu. All these are equal to each other. Mu dot n transpose v, which also from the definition of transpose is equal to u dot m transpose n transpose v. Therefore, this matrix is equal to this matrix. So nm transpose is equal to m transpose n transpose. So how to deal with components? This is the matrix, has components I and j. The ith row and the jth column of this matrix is equal to mji. N, a matrix N multiplied by a matrix M. This is a matrix that has components ij. This is equal to m I, m, j, and in the middle there is a summation over k. And the summation is implied. Now what happens if I use the transpose of one of them? If I say n, m transpose, this is a matrix, this is ij, I will write both matrices I appears first, then I should be summing over K, Kj, but this is the transpose, so this will be J, and the summation is over K, which is implied. The determinant of a matrix will be equal to, if you do the calculation for the determinant, is equal to the determinant of the transpose of the matrix. So, if the determinant of the matrix is not equal to 0, then we know that M is invertible. What does M invertible mean? It means the following. If this is X, then there's a matrix M. There's a vector here, it's called Mx. For every Mx, I can find another matrix. I'm going to call this matrix M minus 1. It's not 1 over M, it's just a matrix that I call M minus 1. This matrix, when it's multiplied by this vector, it will bring me X. Which means that M minus 1, M multiplied by X will be equal to X. Therefore, M minus 1, M is the identity matrix. And this applies also for M minus 1. So if the determinant of M is not 0, then M is invertible, and there exists another matrix that I call M minus 1, such that M minus 1 is equal to M minus 1, M is equal to the identity matrix. It's equal to the identity matrix because it takes a vector X, you multiply by M, you get Mx. The matrix is invertible, so you can come back and get X again. We know that the determinant of I is equal to 1. The determinant of M minus 1, M is equal to the determinant of M minus 1 multiplied by the determinant of M, which is equal to 1, which shows that the determinants are the determinant of M minus 1 is equal to 1 over the determinant of M. The inverse of the matrix, you should, I'm not going to ask you to invert a matrix in an exam, but you should know how to invert a matrix if it's invertible. The inverse of if M is equal to A1, A2, A1, B2, then M minus 1, and M is invertible, M minus 1 is equal to 1 divided by the determinant of M. Multiplied by this. If M is equal to A1, A2, A3, A1, A2, A3, C1, C2, C3, then M minus 1 is equal to 1 divided by the determinant of M multiplied by the following. A vector B cross C, a vector C cross A, and a vector A cross B. But again, you don't have to memorize anything or spend your time trying to invert a matrix. You just need to understand what's the inverse of a matrix is. So, when we start studying stresses, stresses are forces divided by areas, and we're usually interested in forces divided by areas before an object is deformed, and then forces divided by areas after the object is deformed. So we're always interested in what a matrix does for an area. So I'm interested in the area W cross V that is obtained using the cross product between W and V. From the results of the determinant, I know that given any, so if this is a vector W and this is a vector V, and this is a vector MW after transformation, this is the vector MV after transformation, I'm interested in the relationship between A and N, where N is a unit vector perpendicular to the original area, and a small area N and small vector N, that's A is the new area and N is the vector perpendicular to the area after transformation. So I'm interested in the relationship between those vectors and those areas. So what I know is that the determinant of M is equal to the volume after deformation divided by the volume. Now the volume, I don't have a volume here, I'm looking at an area, so I'm going to select an arbitrary vector U. M U M MV cross MW. This is the volume after transformation divided by the volume before, which is U dot V cross W. Which tells me that the determinant of M multiplied by U dot V cross W is equal to MU dot MV cross MW. Which tells me that U dot, this is a number, I can just multiply it by the second vector. And using the definition of the transpose, and since U was arbitrarily chosen, the vector, the determinant of M multiplied by V cross W is equal to the vector M transpose MV cross MW. Now what's V cross W? V cross W V cross W gives me this area in the direction of the unit vector in the original area. So this is A N. This is equal to M transpose multiplied by MV cross MW. MV cross MW is equal to the small a multiplied by N. And so the relationship between A and N and E and N is equal to this. So E and M, the small area multiplied by N, is equal to M negative transpose, the determinant of M, A N, and this is called Nansen's formula. formula again when we study something called the Kirchhoff stresses. At the end of chapter 2. So, perhaps maybe I'll give you another 5 minutes because I'm seeing a lot of sleepy eyes. So, I will start exactly in 5 minutes. So it's 9:33, I'll start at 9:38.